Okay, so we're going to be talking about one of probably the most direct application of one dimension kinematics, and that's freefall. So if you don't remember, freefall, you can see it all the time, right? Whenever you drop something on the ground, whenever you shoot something like a basketball, right? If you toss something, the object will be in freefall. So let's kind of picture that in a diagram. So let's say I have this right here, this ball. And what I'm going to do is toss it in the air, straight up. So it's going to go up here, and then it's going to reach a maximum height, and then it's going to go all the way down, right? I'm drawing it not straight up because I'm going to track its motion on the way up and on the way down. We're going to look at what it looks like. But in reality, picture me just drawing something up and then going straight down the same way it came. So I will throw it up with this velocity right here, right? I'll use blue for velocity. We want to track exactly what's changing as the ball goes all the way up and all the way down. So the acceleration is always going to be pointing down, right? And it's always going to be the same number. So let's look at it here. At this place, the velocity and acceleration are opposing each other, so the object must slow down. And it slows down just a little bit, right? It just slows down maybe like that much. Oops. There we go. And so the acceleration is also the same. It will always stay the same, right? It's always constant, so that's easy to keep track of. What about here? Here the velocity also goes down, so it goes down, and then the acceleration will be the same. And then at the top, this is probably an important landmark of the free fall. This is the point where the velocity is 0. The velocity is 0. But the acceleration is still also pointing down, right? Same, it's always constant. Now we want to track what's basically at the same level at the same place at these points. So at this point, the velocities start going down, right? It's going to start speeding up because they're pointing in the same direction. And then here it's going to even speed up more, and it's going to speed up more, with the acceleration being the same, right? Acceleration, this, and this. It's always that same length. One thing to notice is that this and this have the same size, so I drew them on purpose with the same length, but they're just in opposite directions. So it's kind of symmetric towards in that kind of way. Right? This is symmetric to this, but it's just in the opposite direction. So now we look at some examples of free fall. So here's an example. Let's say I drop a pencil from a height of 3 meters up, right? How long will it take to hit the ground? Ignore air resistance. This is kind of weird because we're not really given too much information, but what I can do is I can just pretend this is 3 meters and I drop a pencil, right? Like that, right? What kind of information do we have? So of course, like always, we should use a table, right? Use a table of values. What else? All these values we should keep track of. We know that it's going to change in height 3 meters, right? But specifically it's negative because its final height here, let's say this is at 0, and its initial height's here, 3. So it's final minus initial, which equals negative 3 meters, right? It seems like that's the only information we have, but actually, we have a lot more information here that you probably, we probably haven't really seen it yet. And these are kind of like implied-ish. So if I drop something, right, it's dropping from rest. So that means its initial velocity is 0 meters per second. Another piece of information that's always not usually given is acceleration. On Earth, we have acceleration and gravity, so it's equal to negative g, which is equal to negative 9.81. A lot of people like to approximate it to 10. So I'm going to do that here. So even with this simple statement right here, we're only given one piece, but these two informations are usually given because I dropped it. I didn't throw it, I dropped it. And then this is usually always given, implied that you know this is a thing. So let's go ahead and solve this. The equation I want to use is probably this one. So we can see that this is 0, so it goes away. And then we can just plug in what we know, right? -3 meters, or -3 equals 1/2 a, which is -10 in this case, t squared. So then I simplify it through, I get this, and then I get 3/5 is equal to t squared, and then on my calculator, I'm just gonna solve it on my calculator. 3/5 square root of 3/5 is it's about 0.775 seconds. So that's how long it will take. So we're going to do one more example. Alright, so this is the second problem. If I throw a ball in the air at an initial velocity of 10 meters per second, what is its peak height? Ignore air resistance. So again, these problems don't like to give us too much, but we actually can find out a lot more based on it knowing that it's free fall. So let me just write out what we're given. We need to find this, we know this, and we also know this, right? I'm going to approximate it to be -10 in this case. That's all they give us, it seems like, but actually they give us another piece of information. Remember with our diagram, if I were to throw a ball like that, this is a landmark point, and because it's at its peak height, we know its velocity here is 0. So this is a piece of information that's like implied, but this is always true, so if you want to find it. But you also have to know that this is the initial and this is your final location in this case. If your final location was here, we can't use v equals 0. So let's go ahead and solve this. So what kind of equation can we use to find height? Let's see. We're not given any time, so we can't use this one, the one that I like to use a lot. We cannot use this because we're not given time, so we should use the other one, which is v squared equals v naught squared plus 2a delta y. Alright, so this is not too bad. We just plug in 0 squared, we plug in 10 squared, which is 100, we plug in 2 times -10, and then we want to find this, right? This is the quantity we want. So now we just start solving for it. So I'm going to bring the 100 over here. -100 is equal to -20 delta y. So that means delta y is equal to 100 divided by 20, or it's 5 meters. So we found what the peak height was, just given one piece of information, and then the other two were kind of implied. So that's kind of the idea of free fall. So let's go back to our diagram. You see that we have 3 landmark points: the beginning, the end, and then the peak height. The acceleration will always be constant, so it's always going to be doing this, always going to be pointing down with the same length. The velocity is the thing that changes in response to that acceleration, right? Right here in the first half, it's slowing down because they're pointing in opposite directions, and then once it reaches this landmark point, you now point in the same direction, so the object is speeding up downwards. And again, we usually like to define a to be the -g, which is 9.81 meters per second squared, also known as, if you want to approximate it, -10 meters per second squared, where g is kind of like the gravity on Earth. If we were on different planets, it would be different measurements, and we'll definitely see those examples maybe in the future, especially when we look at gravitation at the end of this course. So gravitation's in Unit 7. But the idea is this free fall, in this case kinematics on Earth. Usually it's going to be on Earth. So that's it for free fall, and that's pretty much all of one-dimensional kinematics that I can describe of. So now we're going to be looking at two-dimensional kinematics in the next video.